Infectious diseases. The list of killers reads like a rogues gallery. The dreaded Ebola virus, the worldwide killer AIDS, the much-feared SARS, and the recent breakout known as avian flu. All threaten mankind. Men and women on the front line of medicine fight tirelessly for cures. But could the biggest clues actually lie in the past? Because there are some people who should have died from these diseases, but didn't. Can modern science unearth the secret of their survival in time to save future lives? Death, malaria, tuberculosis, and the constantly evolving flu virus. Throughout history, infectious disease has been the planet's #1 killer. Today, the threat is as great as ever. As world leaders brace themselves for the next disaster, some scientists are turning to the past in search of answers. Dr. Stephen O'Brien is a medical detective. His work is part of a global struggle to find new ways of fighting infectious diseases. Diseases that have the potential to kill millions. For Dr. O'Brien, the quest for cures is not just a professional one. For him, it's personal. AIDS killed his brother in 1994.
Losing a brother to AIDS has clearly focused my concentration in seeing people struggling and reaching for hope. It sort of crystallizes your resolve to get to the end of the study and not worry about the details or the vagaries and the niceties of the process.
Dr. O'Brien's come to believe that within our own DNA may lie the key to fighting the diseases which threaten us all. And he's made it his mission to find it.
We might be able to discover natural, hardwired defenses that scientists couldn't have thought of, but which nature did.
He believes that the place to look is among the survivors. People who have witnessed death and suffering on a scale we can barely imagine. Who came into contact with deadly infection, yet lived. Did they manage to pass on their immunity to their descendants? In the winter of 1665, the Great Plague swept through London, killing 1/3 of its population.
The effect of the plague was as devastating as a biological weapons attack would be on a modern city.
And yet out of the devastation came super survivors. Men and women mysteriously resistant to this deadly disease.
Why did they survive? Why didn't everybody die?
Now, through a series of groundbreaking experiments and archaeological discoveries, one man is hoping to find the answer. Do the descendants of the super survivors walk among us? And what can we learn from them?
They would have maybe 15 or 20 doctors just literally staring at me and scratching their heads. Everyone I knew was sick, and I wasn't sick.
Does the Great Plague hold the key to surviving today's infectious diseases? O'Brien's quest will take him across continents and centuries. He believes that from these bleakest of times in history may come the brightest of hopes in the modern battle against disease. Dr. O'Brien thinks analysis of these times may just provide pivotal evidence.
I can't think of an epidemic quite so devastating that we know about in history until you reach back to the Great Plague.
December 1664, London, England. A city on the verge of disaster. In the neighborhood of Southwark, a clergyman named John Allen traveled to the home of the Phillips family. Mary Phillips had suddenly been taken ill. She had a fever. She was delirious. Allen was a physician as well as a priest, and one specific symptom made him very afraid. On Philip's neck was a huge dark boil, a bubo. Allen prayed for her soul, for the people of the city, and for himself, because he knew the plague had returned to London. In the 17th century, no one knew what caused the devastating bubonic plague.
To them, plague was a disease of bad air, what they called a miasma, a mysterious illness-creating substance that spread through the atmosphere. It was a complete mystery to them.
London physician and priest John Allen and those like him knew enough to be terrified. The effects of the plague had been documented for centuries. 300 years earlier, the disease known as the Black Death had first swept through Europe, leaving as many as 30 million people dead. And it kept returning.
There were waves of plague that ravaged Europe almost every generation up until the Great Plague of the 17th century.
Each time, the symptoms were the same: fever and the mysterious black inflammations. Death occurred within a matter of days. By the mid-1600s, John Allen's city was once again under attack.
In the winter of 1664 and the spring of 1665, London was a disaster waiting to happen. It's one of the largest cities in Europe, probably 400,000 people. There is a teeming mixture of all sorts of people, from the very, very wealthy, the aristocrats, the court, down to the marginal figures, the beggars, the vagabonds, the watermen transporting people over London. All of the waste disposal from those 400,000 people goes into the River Thames. Most of the water that community drinks comes out of the River Thames. You can imagine the sort of cycles of infection and disease that are there as endemic all the time.
Throughout the following year, Allen documented death on an extraordinary scale. Bills of mortality, weekly records of the dead, were nailed up in public places.
In an average week, one might be expected to bury perhaps 3 to 5 people. In an average week in the plague period, you would be expected perhaps to bury 200, 300. In some of the suburban parishes, perhaps even 800 people a week. Now that's a lot of dead bodies.
Yet in the midst of it all, a mystery. The plague killed many people, but it didn't kill them all. Some people emerged unscathed, despite living side by side with the dying. In their survival, medical detective Dr. Stephen O'Brien sees an extraordinary opportunity.
But why did they survive? Why didn't everybody die? Why is it that 2/3 of the people in London survived?
To stop an infection spreading, you have to understand how it spreads. 17th century physician John Allen saw hundreds of cases. Can modern scientists learn from the unflinching descriptions of men like him? Dr. O'Brien believes these accounts may hold vital clues.
During the Great Plague, there were chroniclers of the infections that were describing in some detail the medical characteristics of the epidemic. And in many ways, today's scientists are really standing on the shoulders of these early observers, these medical giants, if you will.
The raging thirst, the fever, the delirium. Most of all, the agonizing black swellings. Accounts of these symptoms allow today's scientists to put a name to this disease: the bubonic plague.
It is a disease that is caused by a bacterium called Yersinia pestis that was discovered really in the late 19th century.
The bacteria followed a complicated path. They are initially carried by infected rats. A flea bites a rat and picks up the bacteria. The flea then infects a human being. The plague bacteria are deposited into the victim's skin and move quickly to lymph glands nearby. The bacteria multiply and cause the glands to swell. They spread through the lymphatic system, eventually reaching the heart. At this point, they enter the bloodstream and are spread around the entire body. Vital organs shut down, and the patient dies. But the disease does not die with them. The bacteria want to multiply, so moments before the victim dies, the plague makes its final move. It finds a way to leap from human to human.
Once bubonic plague became established in a very close community, a number of cases would develop pneumonia and cough up the organisms, and subsequent cases would pick that up as pneumonic plague, in other words, plague in the lungs. Now one person can affect another, and the mortality of pneumonic plague is greater than 90%. Its effect upon a population would be devastating.
When pneumonic plague strikes a population, it should kill 9 out of every 10 people it infects. The death toll in London in 1665 was massive. It reached 150,000 people, a third of the population. But it should have been far, far higher.
You would expect the disease to go on and on and on and devour that community, but it doesn't.
This is the most enduring mystery of the Great Plague. How did so many people come into contact with one of the most deadly bacteria ever known and survive? Scientists such as Dr. Stephen O'Brien want to know why so many people survived the Great Plague. But for years, the question was brushed aside. The theory was simply that the outbreak was largely confined to London's underclass. But was survival really just a matter of wealth? A chance discovery in London in the mid-1980s put the theory on trial. In the heart of the city, workers digging on the side of an old church uncovered 57 skeletons. They had been perfectly preserved by deep, heavy clay. These bodies had been dated to the time of the Great Plague. Each skeleton has been subjected to rigorous forensic examination to determine cause of death, age, and social status. Were these victims rich? And did they, in fact, die of bubonic plague?
This individual is a female, probably mid-30s to early 40s. There is no sign of actual pathological disease on the skeleton, so up until the time of death, she was relatively healthy. The plague would have occurred far too quickly to actually make any visible sign on the skeleton.
Evidence suggests that whatever killed these individuals was too swift to leave marks. It wasn't violence or prolonged illness. It took people of all ages. These clues point to plague. So were these victims also members of London's underclass? A biological anthropologist can tell a lot about a person's social status from their bones. A tough life will leave its mark. The examiners looked for signs of deprivation, hard work, and the traces of diseases associated with poverty.
During that time period, it is possible to see diseases such as tuberculosis or syphilis. There's no indication of that on the skeleton at all. Other diseases that might be indicative of working class individuals is arthritis, which is not indicated on this particular skeleton.
There are none of the signs you'd expect to see on the bones of someone who lived in poverty. And there's an even more compelling piece of evidence: the burial itself. If these were poor plague victims, they would most likely have been buried in mass graves.
This person, based on where they were buried within the church, was not a poor individual. They were buried within the church in an individual grave, and that didn't occur among the poorer classes. They couldn't afford to do that. So this was certainly somebody that had some kind of social status at that time.
All 57 skeletons found seem to belong to people from the upper classes. Their discovery and others like it call into question the argument that wealth was any real protection against bubonic plague.
That argument that the poor are the greatest and really the only casualties of the plague epidemics, I think has shown to be flawed.
I think every time an epidemic begins, people who watch it hope that it's going to be limited to a few individuals. With time, I think all of these diseases begin to show that they do not respect class, they do not respect social status, they do not respect ethnicity, they do not respect age, they simply spread whenever they get a chance.
But if social class is not the answer, then what makes the difference between a victim and someone who survives? And can this centuries-old secret shed new light on today's deadliest threats? More than 3 centuries apart, Dr. Stephen O'Brien and the clergyman-physician John Allen share the same goal. They want to understand why some people seem to be shielded from infectious diseases, and they want to find a way to harness that natural power to save others.
Why is it that 2/3 of the people in London have survived and 2/3 of the people in Europe survive? When people get infected with something like HIV, 95% of them die within 10 or 15 years.
Just as we do today, the scientists of the plague era fought desperately to find a cure. At one point, John Allen genuinely believed he had found one: a potion based on a secret recipe.
I myself have taken to drinking a vial of my elixir to ward off the evils of the pestilence. It has, thanks be to God, preserved me from the grave.
Pioneers of medicine were simply tinkering around and trying to think of better ways to develop treatments or elixirs, if you will.
Modern scientists have tended to write off the work of men like Allen as amateurish or superstitious. But is it possible that he was right? Could the medicines of the day be what made the difference between living and dying?
Scientists never know what their research is going to provide, otherwise they wouldn't have to do it.
And Allen was not alone. Hundreds of would-be healers proclaimed that they had found the answer. They offered their own potions, therapies, and masks stuffed with spices that would allow the wearer to breathe bad air and emerge unscathed. Some of these treatments have evolved and have their modern equivalents. But scientists have spent years testing ancient medicines and agree that most would have afforded little protection against the plague. Allen himself knew this. He had learned the hard way. On the 15th of June, 1665, he lost one more of his patients, his own brother, Peter.
I'm sure the plague approacheth me, for it has pleased God to take from me the best friend I ever had in the world. 'Tis my brother, Peter, who was abroad on Lord's Day last in the morning. Towards the evening, a little ill, then took something to sweat, which night brought a stiffness under his ear, where he had a swelling. He died Thursday last.
Dr. Stephen O'Brien also lost someone close to him to infectious disease. His brother Danny died from an AIDS-related illness. He respects Allen's attempts to find an answer.
I don't sneer at people who are trying to be creative and looking for novel solutions.
But if it wasn't the elixir, what prevented Allen, who was exposed to hundreds of victims, from contracting the disease himself?
One of the remarkable facts about Allen's life is that despite being intimately involved with the dead and the dying, he survived. Unlike many other doctors that he knew, he went on to live to a ripe old age of 64. He died in the mid-1670s. So there was something about him and others like him that meant he was resilient or immune.
Dr. O'Brien has come to wonder whether men like Allen did carry the key to combating deadly diseases, not in the form of some miraculous potion, but within their own bodies.
Did these people carry, unbeknownst to them, specific genetic endowments that they'd been handed down from their ancestors that allowed them to defend a little bit better against that bacteria from that flea, from that rat that had bit them and infected them? Did these people develop natural defenses that they passed on to their generations, waiting for the next outbreak to come along?
Science has shown that surviving the plague wasn't down to social class, or hygiene, or medicine. But could it have been directly related to genetics? Of the thousands of genes the survivors carried, was there one which could provide immunity to certain infections? And can Dr. Stephen O'Brien and his colleagues find it? In the early 1980s, a medical disaster struck which would radically alter the way researchers looked at infectious diseases. AIDS hit America's cities.
Although our original and first detection of the AIDS illnesses was in the community of gay men, there was a second population that became infected at around the same time, but for a very different reason. And these were young boys who were born with the blood disease hemophilia.
Hemophilia is a condition where the blood can't clot properly. Sufferers live under the constant threat of fatal internal bleeding. They rely on regular injections of a clotting agent called Factor VIII. In the 80s, this put them at particular risk from HIV because Factor VIII was extracted from donated blood. And any one unit of Factor VIII could contain blood products from hundreds of donors. If just one of those people had HIV, then the entire batch was contaminated. The result was the accidental infection of a large number of hemophiliacs.
The hemophiliacs were carrying a virus that was very deadly, killing 90% of the people that infected. More deadly, if you will, than a bullet to the head.
But as with the Great Plague in London, some people who should have died didn't. Bill Jameson is one such survivor. He saw firsthand what HIV/AIDS was doing to the people around him.
It turned out that the products that we used to actually control our bleeding were actually the products that would turn out to kill most of us.
Like every hemophiliac, Jameson was faced with a terrible dilemma. Take the Factor VIII and risk dying of AIDS, or don't take it and face the possibility of bleeding to death. Jameson assumed that he would contract HIV and die.
I would go in, they would have just literally staring at me and scratching their heads, trying to figure out, this guy took this product, everybody else is positive, but you're as healthy as an ox. And that was the big question.
The same question intrigued Dr. O'Brien.
I wondered whether or not there was a difference in certain genes that allowed them to defend and clear the virus more efficiently than the individual who did become infected.
He soon began what some called a fishing expedition. A mutated gene in 25,000, which would make people like Bill Jameson resistant to AIDS.
Most mutations, particularly when they occur inside of genes, are not very good for you. It's a little bit like taking a hammer to the engine of a Mercedes-Benz and just whacking something. Well, most of the time you do damage. Maybe one time in a million you might do some good and make the car run a little bit better.
It was 2 days before Thanksgiving in 1997 that I got a call from my treatment center, and they said, Bill, you know, we found out why you never became HIV positive. I said, well, okay, you know, let's find out what this big mystery is.
As it turns out, Jameson had inherited a genetic mutation. They called it Delta 32. When HIV infects a normal cell, it does so by latching onto a protein called a receptor. This receptor is the virus's doorway into the cell. In Bill Jameson's case, the Delta 32 mutation means there is no receptor and no way for HIV to enter the cell. The infection is stopped in its tracks. After years of searching, had Dr. O'Brien and his colleagues finally found what they were looking for?
When we first discovered CCR5 Delta 32, it was a whopper. It was basically the equivalent of pulling out a 300-pound marlin out of the sea on our fishing expedition, because it caused complete resistance to HIV in all of the people who carried 2 copies of it, one from each parent.
They now understood what the mutation was, that you inherited it from both parents, and that it gave you immunity to HIV. But to help non-carriers, they wanted to harness the power of Delta 32. That meant understanding everything about it. Why did some people carry this mutation? Where did it come from? According to the theory of evolution, mutations are produced by mistakes in the genetic code. If they provide a positive benefit to the carrier, they survive into the next generation. So Delta 32 must have helped previous generations in some way, long before AIDS arrived on the scene.
We were looking for some sort of breathtaking, cataclysmic event that basically wiped out millions of people, but differentially, according to whether or not they carried this gene. We thought it probably was an infectious disease of some sort, like HIV, but we knew it wasn't HIV/AIDS because that disease has only been around for less than 2 generations.
The answer, again, lies in the DNA. Because if you know how to read the genetic code, it will point to the time in the past when the mutation was most vital. When carriers survived and non-carriers didn't.
The length of the segment around the Delta 32 is a surrogate, if you will, for time. So we examined that variation. We estimated the time elapsed since Delta 32 was last strongly favored. And that number came up to be 700 years, smack in the middle of the 14th century.
This is a vital piece of evidence. Delta 32 had a significant impact in the middle of the 14th century, the time when bubonic plague, the Black Death, first struck the populations of Europe.
The Black Death was probably the greatest epidemic in history. Something of the order of 25 to 30 million Europeans have died.
Dr. O'Brien began to wonder if Delta 32 carriers were better equipped to survive bubonic plague, and that was when he connected another part of the puzzle. The last major outbreak of bubonic plague in Europe was the Great Plague of 1665. A much higher proportion of people seem to have survived that epidemic than survived earlier outbreaks of the disease. Is this evidence of the Delta 32 mutation at work?
It could have been that the survivors of the Black Death passed down genes that protected their descendants from the Great Plague of the 17th century.
If Dr. O'Brien is right, Delta 32 doesn't just confer immunity to AIDS. It could be even more powerful than that. Dr. Stephen O'Brien's next step is to try and find a group of people who are directly descended from plague survivors. If the theory is correct, tests will show that a high number of them are Delta 32 carriers. The challenge is tracking these people down. In the centuries since the Great Plague, London has changed immeasurably.
Because there's a lot of migration in human populations in and out of London, you're going to get other genes coming in and genes going out from the gene flow.
Very few people in today's London can trace their ancestors back as far as the time of the Great Plague. And that is a major block to Dr. O'Brien's success. If he's going to demonstrate the power of Delta 32, he has to find a community where people can trace their ancestry right back.
We were looking for a town which had been succumbed to the disease, but which had not really changed much in terms of immigration of people in and out, a time capsule, if you will, of the survivors of the actual event.
And after years of searching, he found one. 120 miles north of London, deep in the valleys of England's Peak District, lies the small village of Eyam. 3 centuries ago, the plague hit Eyam and is still remembered today. It came on the 9th of August, 1665. To the south, Londoners were dying in their thousands. But so far, Eyam had been spared. What the villagers didn't know was that a biological time bomb was about to be planted among them. A traveling salesman named George Vickers arrived from the capital. He had come to sell bales of cloth. Needing a bed for a few nights, he was welcomed into the home of the Cooper family.
Mary Cooper?
For days, everything seemed normal. Vickers went from house to house, selling cloth and tailoring clothes. But on the night of the 2nd of September, Mary Cooper heard her houseguest screaming. Vickers had a fever. He was vomiting blood and bleeding from the nose. 5 days later, he was dead. And he was just the first. 10 days later, Mary Cooper's infant son died. The villagers realized what was happening. The parish priest called a meeting. As more and more people became sick, the healthy gathered together. They made a decision of tremendous courage. In the full knowledge that they might be sentencing themselves to death, they decided to place the village in quarantine.
It's all around us. All around us.
No one would try to run. No one would leave or enter Eyam until the epidemic had run its course.
In an incredible gesture of self-sacrifice, the population of Eyam sealed off the village in order to stop the plague spreading further. So what we have is a very small, tightly knit community, which remains a tightly knit community to this day, where they were completely able to control people coming in and out of the village.
For Dr. Stephen O'Brien, this event has huge scientific importance. While many small towns suffered the plague, the story of what Eyam went through has been meticulously recorded. Not only that, but many of the people living there could trace their roots all the way back to the 1665 outbreak. For Dr. O'Brien's purposes, Eyam is perfect.
When I first learned about Eyam, where most of the people that lived there were descended from the survivors directly, I became very fascinated with what I perceived as a scientific opportunity.
Every year, the descendants of the plague survivors take part in a procession to keep alive the memory of their ancestors' bravery. Joan Plant is one of them.
I first heard that we were related when we put together this family tree and traced it back to Margaret Blackwell, who was a famous heroine, if you like, in the plague.
Margaret Blackwell's story has become part of Eyam's folklore. She had lost 5 members of her family when she herself fell ill. It is said that one day she staggered from her sickbed, entered the kitchen of her home, and either out of delirium, thinking it was water, or out of desperation, thinking it would end her life more quickly, she drank a jug of hot bacon fat. She vomited and collapsed. But then, somehow, she began to get well. She recovered.
And I asked Joan if she believed that the bacon fat had actually saved Margaret Blackwell, and she said she thought it probably did. And I told Joan I thought I had a different idea.
Dr. O'Brien believes that Margaret Blackwell was one of the lucky ones, that she had inherited Delta 32 from both her parents, and it had saved her life. If he's right, if the mutation did save her and the other survivors, many of their descendants should carry it. Will O'Brien get his proof? Is the ability to fight off killer infections actually being handed down from generation to generation? And is it possible to harness this power in our own modern battle with infectious disease? The evidence is starting to point towards a genetic link between immunity to bubonic plague and immunity to the HIV virus. If Dr. O'Brien is right, a higher than average percentage of these people should carry the Delta 32 mutation. His plan is to take and analyze samples of their DNA.
And then we take this back to the laboratory where DNA is extracted that is suitable for analysis of any genes we might be interested in or you might give us permission to test.
The DNA of each volunteer is analyzed for the presence of Delta 32. The results seem to confirm Dr. O'Brien's theory.
Yesterday, looking for Delta 32 in that sample we collected from Eyam. We actually collected something like 85 individuals to see who had Delta 32, who had 2 copies, who had 1 copy. And when we genotyped them, we discovered about 15% of them were Delta 32 from Eyam, which is about 50% higher than the surrounding regions around Eyam, which had not had the same history of plague. So that was exciting, and the number of people that had 2 copies was twice as high as we expected.
Although the evidence so far suggests that Delta 32 carriers are immune to bubonic plague, O'Brien needs proof. He's about to perform the test all his research has been leading up to. Under laboratory conditions, the cells have been exposed to the plague bacteria, Yersinia pestis, and the results are extraordinary. Delta 32 does appear to offer immunity.
And if you take normal cells that have the normal parent molecule of Delta 32, a gene we called CCR5, they do take up Yersinia pestis quite rapidly. If you take cells which have the equivalent of delta 32, they're resistant to Yersinia pestis. They do not take it up.
After years of research, Dr. Stephen O'Brien and his colleagues finally appear to have their answer. Delta 32 really does seem to be an almost miraculous mutation. It protected people from bubonic plague for centuries in Europe. And carried by their descendants, it has also helped defend against the modern plague of HIV/AIDS. Now that scientists understand how Delta 32 works and where it comes from, they are beginning to learn how to mimic its effects.
So if we could discover why patient A fights off AIDS or Ebola or SARS or bird flu and patient B doesn't, then we could imitate the process by developing new pills or therapies or drugs that we can give to the patient who wasn't lucky enough to be born with them.
This new generation of medicines is already being tested. Spike Rhodes has been HIV positive for 20 years. He was close to death when he was given the chance to try the first in a new class of drugs called fusion inhibitors. Just like Delta 32, they stop the virus by blocking the portal through which it enters cells. For Spike, the results have been extremely encouraging. The T cells, which support his immune system, began to recover within weeks of first taking the drug.
My T cell counts had doubled, and my viral load had gone undetectable, which was also quite a surprise. And within the next 3 months after that, my viral load stayed undetectable. My T cells had doubled up again. If it hadn't come into my life, I probably wouldn't be here.
AIDS, SARS, leukemia, prostate cancer, breast cancer, Alzheimer's, Parkinson's, the litany of diseases that fill our hospitals. Discovering how these defenses work explicitly, pinpointing the exact gene, giving us a mechanism, well, then we know what to go after. Then we know how to develop treatments that are effective and clear out these hospitals from these chronic diseases that we cannot treat.
We are in the middle of a scientific revolution that could change the way we treat sickness. It's a revolution that began in death and suffering centuries ago. And as threats continue to emerge from all corners of the biological world, it may be the mysteries and miracles of the human body itself that provide our ultimate line of defense.